Welcome back from the break. I am Darren Yanda. I'm an Azure and AI MVP and a Microsoft Regional Director for 13 years. I'm the founder of a consultancy business called Develop, which is a Solaris network partner. Feel free to reach out to me on social media with the Darren Yanda allies. In this module, we show ways you can optimize data warehouse workloads that use the dedicated SQL pools. We cover useful developer features, how to define and use workload management and classification to control data loading, and methods to optimize query performance. Let's get started with Module 2. Our focus for this module will be the optimization of a data warehouse with dedicated SQL pool in Azure Synapse. Here's our agenda. We will start by describing Azure Synapse dedicated SQL pools. Then we will go into understanding the developer features offered by dedicated pools and use data loading best practices and optimize data warehouse query performance in Azure Synapse dedicated SQL pools. Let's go over what Azure Synapse dedicated SQL pools is. Dedicated SQL pools refers to the enterprise data warehousing feature available in Azure Synapse Analytics. Dedicated SQL pools represent the dedicated compute resources required to process data loads and queries for relational big data workloads. The size of the SQL pool is determined by data warehousing units, DWU. Synapse SQL offers both serverless and dedicated resource models, offering consumption and billing options to fit your needs. For predictable performance and cost, provision pools to reserve processing power for data stored in SQL tables. For unplanned or burst workloads, use the serverless always available SQL endpoint. Let's have a closer look at the developer features that can be used with Azure Synapse dedicated SQL pools in the context of customer problems. You need to make it easier for us to specify a set of rows within a query result set and compute a value for each row. So this is a common request. Using window functions to perform calculations over a set of rows is the solution. With windowing functions, you treat groups of rows as an entity. The overclose helps us manage the partitioning and ordering of a row set before the associated window function is applied. Finally, aggregate functions, analytic functions, rows and range closes, and many other capabilities surface as part of the windowing functions. It takes too long to get basic information about the data in a large data set as we're exploring data of a big data set. Approximate execution using hyperlog log accuracy in this case to reduce query latency in exchange for a small reduction in accuracy is the helping hand here. The trade-off works well in situations where data engineers are just looking to get a feel for the data. Let's put this into reality and show you how it works. Here we are in our Synapse Analytics workspace. Tailwind Traders is looking for ways to more efficiently analyze their sales data without relying on expensive cursors, subqueries, and other outdated methods they use today. You propose using window functions to perform calculations over a set of rows. With these functions, you treat groups of rows as an entity. So let's start with the overclose. One of the key components of window functions is the overclose. This close determines the partitioning and ordering of a row set before the associated window function is applied. That is, the overclose defines a window or user-specified set of rows within a query result set. A window function then computes a value for each row in the window. You can use the overclose with functions to compute aggregated values such as moving averages, cumulative aggregates, running totals, or a top and per group result. So the first thing we're going to do is to go into the Develop Hub. And from there, we're going to click this plus button to add a new resource. And that's going to be a SQL script for this case. So now that we got the SQL script, we have to make sure our SQL script is targeting our SQL pool, the dedicated pool that we have. So before we go on, I'm going to copy and paste a script that I have prepared previously. So let me do that. And before we go into looking into the script, let's run this and see the result. And there we go. When we use partition by with the overclose, we divide the query result set into partitions. The window function is applied to each partition separately, and computation restarts for each partition. The script we executed uses the overclose with the row number function. And there it is. With the row number function, it displays a row number for each row within a partition. The partition in our case is the region column. The order by clause, on the other hand, specified in the overclose, orders the rows in each partition by the column quantity. The order by clause in the select statement determines the order in which the entire query result set is returned. So let's look at the result that we got in here a little bit. So you can see the region column on the right-hand side, and you see the row numbers on the left. Let's scroll down a little bit. And there we go. So the row number count starts over with a different region every time. Since the partition is set to region, the row number resets when the region changes. Essentially, we are partitioned by region and have a result set identified by the number of rows in that region. So the next thing to look into might be the aggregate functions. So now let's use aggregate functions with our window by expanding on our query that uses the overclose. For that, I'm going to copy a new query in here, make this place a little bit bigger because this one is a little bit bigger as well. So we have replaced the query with a new script. We have some new aggregate functions in there. Before we go into there, let's again run this one and see the result. Okay, there we go. Cool. So in this query, we added sum, average, count, min, and max aggregate functions. Using the overclose in this case is more efficient than using subqueries. Another topic to look into is the analytic functions. Analytic functions calculate an aggregate value based on a group of rows. Unlike aggregate functions, however, analytic functions can return multiple rows for each group. Use analytic functions to compute moving averages, running totals, percentages, or top end results within a group. Tailwind Traders has book sales data they import from their online store and wish to compute percentages of book downloads per category. To do this, you decide to build window functions that use percentile count and percentile disk functions. For that, I'm going to copy another query that I have ready to go in here. Let's replace this one. And there it is. So let's run this before we look into it. So in this query, we use percentile count and percentile disk to find the median number of downloads in each book category. These functions may not return the same value. Percentile count interpolates the appropriate value, which may or may not exist in the data set, while percentile disk always returns an actual value from the set. To explain further, percentile disk computes a specific percentile for sorted values in an entire row set or within a row set's distinct partitions. The value 0.5 passed to the percentile functions in both cases computes the 50th percentile or the median of the downloads. The within group expression specifies a list of values to sort and compute the percentile over. Only one order by expression is allowed, and the default sort order is ascending. The over clause divides the from clause's result set into partitions, in this case as category. The percentile function is applied to these partitions. Now let's replace this script with another one that I have in here that uses the lag analytic function. Tailwind Traders wants to compare the sales totals for a product over an hourly basis over time, showing the difference in value. To accomplish this, you use the lag analytic function. This function accesses data from a previous row in the same result set without the use of a self-join. Leg provides access to a row at a given physical offset that comes before the current row. We use this analytic function to compare values in the current row with the values in a previous row. So let's run this and see what we're going to get. So our query uses the log function to return the difference in sales. You can see that between the current sales total, the previous sales total, and the difference. So this is the difference in sales for a specific product over peak sales hours, 8 to 20. We also calculate the difference in sales from one row to the next. Notice that because there is no lag value available for the first row, the default value is 0. Now let's look into the rows clause. The rows and range clauses further limit the rows within the partition by specifying start and end points within the partition. This is done by specifying a range of rows with respect to the current row, either by logical association or physical association. Physical association is achieved by using the rows clause. Tailwind Traders wants to find the books that have the fewest downloads by country, while displaying the total number of downloads for each book within each country in ascending order. So to achieve this, you use rows in combination with unbound preceding to limit the rows within the country partition, specifying that the window starts with the first row of the partition. So for this one, I'm going to copy another query to look into, and there we go. So let's run the query first. Here we go. In this query, we use the first value analytic function to retrieve the book title with the fewest downloads, as indicated by the rows unbounded preceding clause over the country partition. The unbounded preceding options set the window start to the first row of the partition, giving us the title of the book with the fewest downloads for the country within the partition. In the result set, we can actually scroll the list of books. And let's go down and see. There we go. So Harry Potter, the Ultimate Quiz book is actually the least selling book in Germany. And if we keep scrolling down, we can see that Burn For Me is the least selling book in Sweden. As Tailwind Traders starts to work with very large data sets, they struggle with slow-running queries. For instance, obtaining a distinct count of all customers in the early stages of data exploration slows down the process. How can they speed up these queries? You decide to use approximate execution using hyperlog accuracy to reduce the query latency in exchange for a small reduction in accuracy. This trade-off works for Tailwind Traders' situation where they just need to get a feel for the data. To understand this requirement, let's first execute a distinct count over the large sale heap table to find the count of distinct customers. Here is our query. And let's run and see how long this is going to take. It took 15 seconds, not that bad. But that is expected, as distinct counts are one of the most difficult types of queries to optimize. So in this case, the result is an exact 1 million. So I'm going to replace the query with a new script that uses the hyperlog approach. So let's run this one. There it is. The query takes about half the time to execute. The result isn't quite the same. In this case, instead of a 1 million, what we have here is 1,001,619. So approx count distinct returns a result with a 2% accuracy of true cardinality on average. This means if count distinct returns 1 million, then hyperlog will return a value in the range of 999,736 to 1,016,234. Don't worry, I read those from my notes. Let's explore the data loading best practices in Azure Synapse dedicated SQL pools. One of the best practices that should be followed is to limit the number of concurrent connections while loading data. If you're unable to minimize amount of concurrent load jobs, allocate fixed resources to workload group. Assign maximum and minimum usage for varying resources under load. These adjustments can be done live without having to take Azure Synapse Analytics offline. Some benefits are the ability to reserve resources for a group of requests, limit the amount of resources a group of requests can consume, providing access to shared resources based on importance level. Being able to set the query timeout value reduces the need for DBAs to run away queries. Finally, monitoring the MVs help query and view configured workload groups. Let's put this into reality and show you how it works. We are back in our Synapse Analytics workspace. So let's talk about workload management a little bit. Running mixed workloads can pose resource challenges on busy systems. Solution architects seek ways to separate classic data warehousing activities such as loading, transforming, and querying data to ensure that enough resources exist to hit SLAs. Workload management for dedicated SQL pools in Azure Synapse consists of three high-level concepts: workload classification, workload importance, and workload isolation. These capabilities give you more control over how your workload utilizes system resources. Let's start with workload importance. So the workload importance influences the order in which a request gets access to resources. On a busy system, a request with higher importance has first access to resources. Importance can also ensure ordered access to logs. Workload isolation reserves resources for a workload group. Resources reserved in a workload group are held exclusively for that workload group to ensure execution. Workload groups also allow you to define the amount of resources that are assigned per request, much like resource classes do. Workload groups give you the ability to reserve or cap the amount of resources a set of requests can consume. Finally, workload groups are a mechanism to apply rules such as query timeout to requests. Tailwind Traders has asked you if there's a way to mark queries executed by the CEO as more important than others, so that they don't appear slow due to heavy data loading on or other workloads in the queue. You decide to create a workload classifier and add importance to prioritize the CEO's queries. Let's go into the Develop Hub and create ourselves a new SQL script. As always, we gotta make sure we are selecting SQL pool, our dedicated SQL pool for this exercise. I'm gonna bring in a SQL query. Let's copy paste that one in. This is gonna help us making sure that there are no queries currently being run by users logged in as ASA SQL workload 01. That's one of the test users we're gonna use. The CEO of the organization is using the workload 01 user, and then we got another user called workload 02 representing the data analyst working on the project. So let's run this one for now and see what we got. Okay, perfect. It looks like there are no queries running in our data warehouse right now, which is a good start. So now we will create some, workload. Some queries. We will hit the data warehouse with some queries. And in order to do that, I'm going to go into the Data Integrate tab to look into our list of pipelines. Here we are. So from these pipelines, I'm going to run the pipeline that is called Lab 08 Execute Data Analyst and CEO Queries. Let's open that one up and trigger. So this is gonna put a lot of queries essentially in a simulated environment, and this will send both CEO and analyst queries to our data warehouse. Now that that is running, let's go back to our SQL script. This time, I'm gonna replace the query with something a little bit different. And let's run this one and see what we got. There we go. So let's maximize this part a little bit to see a little bit more of the information here. As you can see, this query took a while to run because currently our data warehouse is being bombarded with a lot of queries through that pipeline. And if you look at the queries here, all of the queries have the same importance level. So they are all normal importance. And as you can see, there's a mix of queries that are submitted by workload 01 that represents our CEO. And there's a mix of queries running through workload 02 as well, which is the data analyst in this case. Let me copy paste another query that I have in here. So in this case, we will give our workload 01 user queries priority by implementing the workload importance feature. We are executing the script to create a new workload classifier named CEO that uses the larger C workload group and sets the importance level of the queries to high. So let's run this. Here we go. So now we're going to flood the system again. I will go back to the pipeline and click trigger now. Before we do that, let's make sure we don't have a current pipeline running. Okay, the old pipeline is still running. Let's cancel that one. Okay, we got that canceled. So now we can go back and give this another shot. So this time, because we got the classifier, we're expecting to see a different result. So we'll start the pipeline, and we're going to need the same T-SQL code we use to see the queries, right? So I'm going to replace this one again and run to see what's happening. Let's make this a little bit larger. And there we go. You can see that the queries that are belonging to workload 01 that belong to workload 01 have higher priority. So it looks like we were able to give high importance to the queries that the CEO wants to run. Now again, let's go to the monitor tab and make sure we cancel this pipeline because this might take a long time to complete. So let's switch to workload isolation. Workload isolation means resources are reserved exclusively for a workload group. Workload groups are containers for a set of requests and are the basis for how workload management, including workload isolation, is configured on a system. A simple workload management configuration can manage data loads and user queries. In the absence of workload isolation, requests operate in the shared pool of resources. Access to resources in the shared pool is not guaranteed and is assigned on an importance basis. Given the workload requirements provided by Tailwind traders, you decide to create a new workload group called CEO Demo to reserve resources for queries executed by the CEO exclusively. Let's go back to our Develop tab into our SQL query in here. I'm going to copy paste a new query. This script creates a workload group called CEO Demo to reserve resources exclusively for the workload group. In this example, a workload group with a mean percentage resource set to 50% and request mean resource grant percent set to 25% is guaranteed to concurrency. So let's run this one. Perfect. So now that we got our workload group, the next step is to create the workload classifier. For that, I'm going to bring in a new script. So this script will create a workload classifier called CEO Dream Demo that assigns a workload group in importance to incoming requests. The script sets the importance to below normal for the SQL.workload02 user through the new CEO Dream Demo workload classifier. Let's run this. Okay. So we're going to go back to our original script in here. I'm going to copy that back. So this script is just going to help us to see if there are any active queries running by workload 02 user. Here we go. It looks like there are no queries running for user workload 02. So we are good to test things out. So we're going to go to our pipelines list in here. And this time we're going to run the execute business analyst queries pipeline. So I will trigger this one. Now that it's done, let's go to our SQL script and run this query to see what's going to happen. I'm going to make this part a little bit bigger. And there we go. You can see that workload O2 user, all of the queries that are running through that user are now flagged below normal importance. That's exactly what we wanted to do. All the scripts are executed under workload O2 in this case with an importance level of below normal, and we have successfully configured the business analyst queries to execute at a lower importance than the CEO queries. We can also see that the CEO Dream Demo workload classifier works as expected. So let's go to the monitor tab again and clean up the pipeline that we created. So cancel this one. And there we are. We will go to our SQL script back. And I'm going to copy and paste this a little bit longer script. So this script is setting 3.25% minimum resources per request. So configuring workload containment implicitly defines a maximum level of concurrency with a cap percentage resource set to 60% and the request mean resource grant percent set to 1%. Up to a 60 concurrency level is allowed for the workload group. Let me copy paste the formula that you should keep in mind. Here it is. This defines the maximum concurrency you will get. Let's run this. There we go. So now we will flood the system with our pipeline, with the analyst pipeline, for another round. And we will go back to our script and use our classic script to look into the ongoing queries. So let's run that. As you can see right now, pretty much everything is on normal importance. After several moments, it might take up to a minute, we should see several concurrent executions by the ASA workload O2 user running at below normal importance. Let's give this another try. Now, let's scroll down. There we go. So, as you can see right now, some of these queries are flagged below normal, and these are queries that are coming from workload O2. Let's explore query performance optimization in Azure Synapse dedicated SQL pools. A distribution is the basic unit of storage and processing for parallel queries that run on distributed data. When SQL Analytics runs a query, the work is divided into 60 smaller queries that run in parallel. Each of the 60 smaller queries runs on one of the data distributions. Each compute node manages one or more of the 60 distributions. A SQL pool with maximum compute resources has one distribution per compute node. A SQL pool with minimum compute resources has all the distributions on one compute node. We will discuss three table distributions in detail. A round-robin table is the simplest table to create and delivers fast performance when used as a staging table for loads. A round-robin distributed table distributes data evenly across the table but without any further optimization. A distribution is first chosen at random and then buffers of rows are assigned to distributions sequentially. It is quick to load data into a round-robin table, but query performance can often be better with hash-distributed tables. Joins on round-robin tables require reshuffling data, which takes additional time. Consider using the round-robin distribution for your table in the following scenarios. When getting started is a simple starting point since it is the default. If there is no obvious joining key, if there is not good candidate column for hash distribution in the table, if the table does not share a common join key with the other tables, if the join is less significant than other joins in the query, when the table is a temporary staging table. A hash-distributed table can deliver the highest query performance for joins and aggregations on large tables. To shard data into a hash-distributed table, SQL Analytics uses a hash function to deterministically assign each row to one distribution. In the table definition, one of the columns is designated as the distribution column. The hash function uses the values in the distribution column to assign each row to a distribution. Consider using the hash distribution for your table in the following scenarios. Distribute the rows based on the value in the distribution column, using a deterministic hash function to assign each row to one distribution. Is designed to achieve high performance for queries that running as large fact tables in a star schema. Choosing a good distribution column is important to ensure the hash distribution performs well. As a starting point, use on tables that are greater than 2 gig in size and has frequent inserts, updates, and deleted. But don't choose a volatile column for the hash distributed column. Replicated table provides the fastest query performance for small tables. A table that is replicated caches a full copy of the table on each compute node. Consequently, replicating a table removes the need to transfer data among compute nodes before a join or aggregation. Replicated tables are best utilized with small tables. Extra storage is required and there's additional overhead that is incurred when writing data, which makes large tables impractical. Consider using replicated distribution for your table in the following scenarios. A full copy of a table is placed on every single compute node to minimize data movement. Works well for dimension tables in a star schema that are less than 2 gig in size and are used regularly in queries with simple predicates. Should not be used on dimension tables that are updated on a regular basis. You can convert existing round-robin tables to replicated tables to take advantage of the feature using a CTAS statement. Let's talk about result set caching. Caching the results of a query in data warehouse storage enables interactive response times for repetitive queries against tables with infrequent data changes. The result set cache persists even if a data warehouse is paused and resumed later. Query cache is invalidated and refreshed when underlying table data or query code changes. Final result set cache is evicted regularly based on a time-aware last recently used algorithm. You should be mindful about a couple of points here though. The maximum size of the result set cache is 1 terabyte. Query results are persisted for a maximum of 48 hours, but can be evicted earlier to save space based on the least recently used result. Disabled on the data warehouse by default unless turned on at the session level or the entire database level. Let's put this into reality and show you how it works. We are back in Synapse Analytics workspace. So let's go to Develop Hub and create a new script for us. And this script will, as always, target the SQL Pool 01, our managed instance, managed SQL Pool. So the first thing we're going to try out is this query, simply getting and counting all of the records on sale heap table. So it took 25 seconds to run this query, and it looks like we got 340 million rows in there. Yeah, that's a nice number. So let's run another query, this one. Let's run this one, which is a little bit more complex. It took 20 seconds to run this query as well. So there's clearly something wrong with the sale heap table that induces the performance hit. Note the option close that we used, by the way. This comes handy when you're looking to identify your query in the DMVs. For example, for this particular query, we can go ahead and query the DMV based on the label and get some information about the runtime and resource allocation and so on. So let's switch to the data tab. And from there, we're going to go into databases. We're going to find our SQL Pool 01, tables, and our goal is to find the sale heap table. Let's scroll down a little bit. Now let me make this a little bit bigger. Can I do that? There we go. Perfect. Okay, .i sale heap table. Yeah, perfect. So this one, I'm wondering what the, what the structure of this table is. So for that, maybe we can go and say new SQL script and create to be able to see how this table is created. You can immediately spot at least two reasons for the performance hit: the round-robin distribution, the heap structure of the table. In this case, when we're looking for fast query response times, the heap structure is not a good choice, as we will see in a moment. Still, there are cases where using a heap table can help performance rather than hurting it. One such example is when we're looking to ingest large amounts of data into the SQL database associated with the dedicated SQL pool. If we were to review the query plan in detail, we would clearly see the root cause of the performance problem: inter-distribution data movements. So data movement is an operation where parts of the distributed tables are moved to different nodes during the query execution. This operation is required where the data is not available on the target node, most commonly when the tables do not share the distribution key. The most common data movement operation is shuffle. During shuffle, for each input row, Synapse computes a hash value using the join columns and then sends that row to the node that owns that hash value. Either one or both sides of the join can participate in the shuffle. Here's a diagram that displays the shuffle to implement join between that implements join between table T1 and T2, where neither of the tables is distributed on join column 2. This is actually one of the simplest examples given the small size of the data that needs to be shuffled. You can imagine how much worse things can become when the shuffled row size becomes larger. Let's go back to the Develop Hub. We have our script on screen. So I'm gonna bring a script and replace this one. Actually, let's close this one. We don't need that anymore. And this one, I'm gonna replace it with this. So let's run that, because that's gonna take a while. CTAS, create table as select, is a more customizable version of the select into statement. Select into doesn't allow you to change either the data distribution, the distribution method, or the index type as part of the operation. You create a new table by using the default distribution type of round robin and a default table structure of clustered column store index. With CTAS, on the other hand, you can specify both the distribution of the table data as well as the table structure type. There we go. So now let's run the same query, but this time against sale hash instead of sale heap. So you can clearly see the performance improvement when we execute this query against the new hash table compared to the first time we ran the script against the heap table. In our case, the query executed in about 7 seconds. Let's talk about improving table structure with partitioning. Table partitions enable you to divide your data into smaller groups of data. Partitioning can benefit data maintenance and query performance. Whether it benefits both or just one is dependent on how data is loaded and whether the same column can be used for both purposes, since partitioning can only be done on one column. Data columns are usually good candidates for partitioning tables at the distribution level. In the case of Tailwind Trader sales data, partitioning based on the transaction date ID column seems to be a good choice. The dedicated SQL pool already contains 2 versions of the sale table that have been partitioned using transaction date ID. These tables are sale partition 01 and sale partition 02. So let me copy paste the code in here. And this is, let me make this a little bit bigger. So these are the CTAS queries that have been used to create these tables, the partition 01 and partition 02. Notice the 2 partitioning strategies we have used here. The first partitioning schema is month-based, and the second one is quarter-based. As you can see, the 2 partition tables are hash distributed. A distributed table appears as a single table, but the rows are actually stored across 60 distributions. The rows are distributed with a hash or round-robin algorithm. There are 3 types of distributions: Round-robin distribution distributes table rows evenly across all distributions at random. Hash distribution distributes table rows across the compute nodes by using a deterministic hash function to assign each row to one distribution. And the replicated distribution fully copies the table and makes it accessible on each computer node. Back to the hash distributed tables, remember that it distributes table rows across the compute nodes by using a deterministic hash function to assign each row to one distribution. Since identical values always hash to the same distribution, the data warehouse has built-in knowledge of the row locations. Dedicated SQL pool uses this knowledge to minimize data movement during queries, which improves query performance. Hash distributed tables work well for large fact tables in a star schema. They can have very large numbers of rows and still achieve high performance. There are, of course, some design considerations that help you to get the performance the distributed system is designed to provide. So, consider using a hash distributed table when the table size on the disk is more than 2 GB, or the table has frequent inserts, updates, and delete operations. Looking at the query, also notice that both partition tables are configured with a clustered column store index. There are different types of indexes you can use in dedicated SQL pool. A clustered column store index offers the highest level of data compression and best overall query performance. A clustered index is performant for looking up a single to few rows, and a heap benefits from faster loading and landing temporary data. It is best for small lookup tables. And finally, non-clustered indexes enable ordering of multiple columns in a table and allows multiple non-clustered indexes on a single table. By default, dedicated SQL pool creates a clustered column store index when no index options are specified on a table. Clustered column store tables offer both the highest level of data compression as well as the best overall query performance. They will generally outperform clustered index or heap tables and are usually the best choice for large tables. For these reasons, clustered column store is the best place to start when you are unsure of how to index your table. There are a few scenarios where clustered column store may not be a good option. Column store tables do not support varchar max and varchar max and var binary max. In those cases, consider heap or clustered index. Column store tables may be less efficient for transient data. Consider heap and perhaps even temporary tables. Small tables such as less than 100 million rows might not be a good fit for column store index as well. Consider heap tables. Let's talk about partitioning a little bit. Again, with this query, we partition the two tables differently, so we can evaluate the performance difference and decide which partitioning strategy is the best on the long run. The one we ultimately go with depends on various factors with Tailwind Traders data. You may decide to keep both to optimize query performance, but then you double the data storage and maintenance requirements for managing the data. The range right option that we use in the query is used for time partitions. Range left is used for number partitions. The primary benefits to partitioning is it improves efficiency and performance of loading and querying by limiting the scope to a subset of data. It offers significant query performance enhancements where filtering on the partition key can eliminate unnecessary scans and eliminate I/O. The reason we have created two tables again with different partition strategies is again to experiment with proper sizing. While partitioning can be used to improve performance, creating a table with too many partitions can hurt performance under some circumstances. These concerns are especially true for clustered column store tables like we created here. For partitioning to be helpful, it is important to understand when to use partitioning and the number of partitions to create. There's no hard and fast rule as to how many partitions are too many. It depends on your data and how many partitions you're loading simultaneously. A successful partitioning scheme usually has 10 to hundreds of partitions, not thousands. When creating partitions on clustered column store tables, it is important to consider how many rows belong to each partition. For optimal compression and performance of clustered column store tables, a minimum of 1 million rows per distribution and partition is needed. Before partitions are created, dedicated SQL pools already divides each table into 60 distributed databases. Any partitioning added to a table is in addition to the distributions created behind the scenes. Using this example, if the sales fact table contained 36 monthly partitions, and given that the dedicated SQL pool has 60 distributions, then the